This is your presenter Asloob Mudassar, and I am presenting slide number 136 of the course on laser physics. Question is, discuss general characteristics of a gas laser system. Also give detailed description of a helium neon and a copper vapor laser system. The answer is, gas lasers involve low density active media. In gas lasers, gases at low pressure, a few tens of torr, are used. Broadening due to collision is small. Doppler broadening is the dominant mechanism and determines the line width of the gas laser. The broadening of energy levels is thus small, a few gigahertz or smaller. Absorption bands do not exist, and the optical pumping by lamps, either CW, that is the continuous wave, or pulsed, is inefficient. Excitation mechanism is by passing large amount of currents through the gas mixture, either continuously or pulsed or at radio frequency. Chemical pumping, optical pumping with another laser are sometimes preferred over the electrical pumping in only specific cases. In gas lasers, stimulated emission is the most dominant process responsible for the decay of excited species from the upper laser level to the lower laser level. There are some other decay processes which do not contribute to the laser beam. They include de-excitation of a species to ground level and excitation of the same or a different species from the ground state during a collision due to the presence of nearly resonant excitation levels. The collision is referred to as near resonant collision. An electron during a collision with an excited species can take up the whole energy as its kinetic energy while leaving the excited species in a lower or ground state, referred to as the superelastic collision. An excited species can lose its energy on colliding with the walls of the container. An excited species may decay spontaneously, which may sometimes result in radiation trapping. That is, an emitted photon is reabsorbed by another identical species. Apart from the near resonant collisions, the decay of the excited species in other categories lowers the performance of a gas laser system. So you see that here we have discussed the possible decay processes which are responsible for the decay of the excited states to the lower states or to the ground states. And these processes, if occur, they are responsible for lowering of the performance of the gas lasers. And the stimulated emission will be the most dominant process responsible for the emission of laser beams from the gas lasers. In the presence of excitation and de-excitation processes, equilibrium population is eventually set up among the laser levels. The following conditions must be satisfied for the CW lasing action to occur. Excitation rate to the upper laser level must be greater than the de-excitation rate to the lower laser level. The decay rate of the upper laser level is slower than the decay rate of the lower laser level. So you see that these two conditions are necessary in order to achieve the population inversion for the continuous wave operation from the laser system. If the second condition fails, pulsed laser operation can still be achieved. So let's see which one is the second condition. That is this one. excitation rate to the upper laser level must be greater than the de-excitation rate to the lower laser level. The decay rate, so this is the condition, the decay rate of the upper laser level is slower than the decay rate of the lower laser level. Because if this is slower, then the population will pile up in the upper laser level, which is necessary for as a population inversion for a CW laser action. So if the second condition fails, the pulsed laser operation can still be achieved, but such a laser system will be self-terminating. All metal vapor lasers, for example lead, copper, etc., are self-terminating and generally operate in the visible part of the spectrum. Noble gas lasers generally operate in the IR, that is in the infrared. Helium neon operates both in the IR and in the visible. So this is what a general view we have given about the gas lasers. Now we are going to talk about the helium neon laser. Helium neon laser, it contains a mixture of two gases, helium and neon. Laser transitions occur in neon. So neon is excitation and de-excitation in the neon is responsible for the lasing action. Neon is excited through the electron collision to its 4s and 5s levels. So 4s and 5s levels are the excitation levels, that is the upper state levels in the neon scheme. So let me show you the diagram also so that you can understand what I am talking about. Indication of laser transitions in a helium neon laser system. You can see that I am plotting the energy level diagrams for the helium and the neon. This is the ground state configuration of the neon atom, 1s2, 2s2, 2p6. And this dotted lines mean that we are jumping from 0 to, for example, 16 electron volt. The rest of them is not important. So here is the collisional excitation. That is, you are going to excite the helium atom from the ground state, which is the 1s, which is the 1s state, to the upper laser states, to the upper level states. For example, which is the 3s1 and 1s states through the collisional excitation. So the helium is excited through the collisional excitation. And then you see that there are two levels which are coincident in energy and very close in energy to these levels of the helium, and these are the 5s level and the 4s level of the neon atom. So these are the upper laser levels. 5s levels is the upper laser level for the 4p level, and the 5s level and the 4s level of the neon is the upper level, stands as the upper level for the 3p states. And you know that the important transitions have been shown. From the 5s, we decay to the 4p states will give you 3391 nanometer wavelength. Then from the 5s to the 3p will give you 333 nanometer. The exact number is 332.8 nanometer. And then from the 5s to 3p again, we have the emission of 543 nanometer. And then from the 4s to 3p, we have 1152 nanometer. So these are four important lasing wavelengths that we can obtain in a helium neon laser system. And then you know that this 3p state will decay, 3p states will decay to the 3s states. So this is what I have given a rough idea. I might be explaining this diagram in more detail. For example, what is 2 3s and what is 2 1s states. These will be explained after a few minutes. So now I am going to explain the diagram of the description of the helium neon laser. So it contains a mixture of two gases, helium and neon. Laser transitions occur in neon. Neon is excited through electron collision to its 4s and 5s levels To increase the pumping to these levels, helium is added, which has its two levels, which is 2 3s and 2 1s, nearly resonant with the two levels of the neon. So these are the two levels of the helium atom, which are nearly resonant with the two levels of the neon, and they are correspondingly 5s level and 4s level respectively. The ground state electronic configuration of the helium is 1s2, or we can write it as 1s 1s. That is, there are two s electrons with quantum numbers L1 is equal to 0, L2 is equal to 0, L1 is equal to 0 for the first 1s, L2 is equal to 0 for the second 1s, S is equal to half, that is the spin quantum number is half for the first 1s electron, and the S2 is equal to half for the second 1s electron. These are the orbital angular quantum number, that's the L1 and L2, and S1 and S2 are the spin quantum numbers. So we have written L1 is equal to 0 for the 1s electron. Similarly, S1 is equal to half for the 1s electron. This is the spin quantum number. And similarly, for the second 1s electron, I have written L2 is equal to 0 and S2 is equal to half. Under Russell-Saunders coupling, which we refer to as the RS coupling, capital L, that is the total angular momentum of the atom, is given by mod of L1 plus minus L2. So substitute the value of L1 and L2, which is 0 plus minus 0 will give you 0. So the total angular momentum of the helium atom in the ground state is represented by capital L, and that is equal to 0, which corresponds to the term capital S. And the spectroscopic symbol that we use for the total angular momentum L to be equal to 0 is represented by capital S. And you know that if capital L is equal to 1, then the term symbol will be capital P. And if capital L is equal to 2, the term symbol will be capital D. So for L is equal to 0, the term symbol is capital S. And this corresponds to the ground state configuration, because we are here 1s2 is the ground state configuration of the helium atom, consisting of two electrons each in 1s and 1s, and we have written their quantum numbers, and then we have written the capital L, which is the total angular momentum quantum number of the atom in the ground state of the helium atom. The two electrons, since the two electrons are occupying the same s orbital, they have anti-parallel spins. That is, one electron will have spin up, the other electron will have spin down, and the total spin quantum number capital S is equal to mod of S1 plus minus S2, which is equal to, we are using only a negative sign over here because the spins are anti-parallel, as we have shown, because they are occupying the same orbital. So the spin must be anti-parallel. So we are using mod of half minus half, which is equal to 0. So the total spin angular momentum of the atom in the ground state is 0. So don't confuse this capital S with this S. This S is actually the term symbol. That is the spectroscopic symbol that we use. And this S is actually the total angular momentum, the total spin angular momentum of the atom in the ground state, because we are talking about the ground state electronic configuration of the helium atom. So this corresponds to a multiplicity, which is a multiplicity is given by capital M is equal to S plus 1. And if we put the value of this S, which is equal to 0 over here, and multiplying with the 2 plus 1 will give you 1. That is the singlet state. So this multiplicity means that singlet state is possible. The total quantum number is then given by capital J is equal to the mod of L plus minus S. So this capital L is the total angular momentum of the atom, the total angular momentum quantum number of the atom, and this capital S is actually the spin quantum number, the total spin quantum number of the atom, of the helium atom in the ground state. So we are combining these two, one plus we are adding or subtracting them together to get the total angular momentum capital J of the atom, which combines the two which combines, which is the quantum number corresponding to the total angular momentum of the atom, and the total angular momentum of the atom is given by the total orbital angular momentum plus the total spin plus minus total spin angular momentum of the atom. And here we are talking about not the angular momentums but the quantum numbers corresponding to those quantum numbers. So capital J is the total quantum number of the atom, capital L is the total orbital quantum number of the atom in the ground state, and capital S is the total spin quantum number of the helium atom in its ground state. So adding 0 plus minus 0, the mod of this one is equal to 0. So this is capital J. The total angular momentum of the atom is also 0. So here we have talked about, you see that three quantum numbers, that is the orbital quantum number and spin quantum number. In atomic physics, you see that here I have also talked about the multiplicity. In atomic physics, multiplicity is a measure of the number of possible spin states. Number of possible spin states. So you see that I shall be covering these things in much greater detail while I shall be discussing the course on atomic physics, which will be the probably the next course. So you see that now I have discussed the total angular momentum. I have calculated the total angular momentum of the total quantum number, total orbital quantum number of the atom. This is the total orbit, this is the total spin quantum number, and this is the total quantum number of the atom. Now let's talk about the ground state. The ground state is represented by the term. This is the term for writing down the ground state of the atom. This n is the principal quantum number. This m is the multiplicity. This j is the total quantum number of the atom, and this s is the term symbol. Don't confuse this as the total spin quantum number. This is a term symbol, and this term symbol corresponds to the value of L. So if L is equal to 0, then the term symbol will be represented by capital S. So I have just written them in the bold so that I can identify it, but you don't need to write it as bold. Only just write capital L and small and capital S without making them bold. So you see that this is what the term symbol S. This S, capital S, corresponds to that the total angular momentum, orbital angular momentum of the atom, which is capital L, is 0. And m is the multiplicity, j is the total angular quantum number of the atom, and n is the principal quantum number. So now I am going to plug in the values over here. So since I am talking about the 1s2 state of the ground state, that is the principal quantum number over here is 1. So I am using 1 over here as the principal quantum number, which is 1 over here. The multiplicity that I have just calculated is 1. So you can see that is 1 over here, and this 0 is the total quantum number j of the atom, which is 0. So 1 is the principal quantum number, this one is the multiplicity, and then this capital S is the term symbol corresponding to L is equal to 0, and this is the j is equal to 0. So this is the ground state configuration. So let me show you that this is what I have. This is can simply be written as 1 and 1s without writing the value of j, because when j is equal to 0, we usually don't represent j for the 0 value. So 1s1 is actually the term symbol corresponding to the ground state of the helium atom. And you see that this is shown over here. 1s, 1s. 1 is the principal quantum number, this one S is the multiplicity, this capital S is the term symbol. So this is the term symbol corresponding to the ground state of the helium atom. During collisional excitation, one of the 1s electrons of the helium moves to 2s. So you see that now we are talking about the collisional excitation, that is maybe excitation through electrons. So during the collisional excitation, one of the 1s electrons of the helium atom moves to 2s and the electronic configuration becomes 1s, 2s. Before that, in the ground state, the electronic configuration was 1s square or 1s, 1s, which I have just talked about. Now, if you have moved one of the electrons from 1s to the 2s, then the configuration becomes this one. So this is the configuration of the excited electronic state of the helium atom. That is the excited state just above the ground state. So 1s, 2s is the first excited electronic state of the helium atom. Here, the two electrons can exist in parallel states as well as in the anti-parallel spins because they are now occupying different orbitals. So this is in 1s, this is in 2s. So the electron in 1s and the electron in 2s, they may have parallel spins or they may have anti-parallel spins because there are no restriction to them. In the previous case, when we talked about the ground state, both electrons were in 1s and 1s. So it was compulsory for them to have the anti-parallel spins. But now they are, when we have excited one of the electrons to the 2s state, now there is a possibility that 1s electron and that is an electron in the 1s and another electron in the 2s, they can have parallel spins or they can have anti-parallel spins. Both possibilities exist. In the case L is equal to 0, because you have quantum numbers. For this 1s electron is L1 is equal to 0. For this 2s electron, again the orbital quantum number L2 is also 0. So you are just combining them to get the total angular momentum quantum number, which is L is equal to 0, as this is the same as for the ground state configuration. And now S is equal to mod of S1 plus minus half. Now we have to include both signs because the possibility is that with the plus sign they have parallel spins and with the negative sign they have anti-parallel spins. So the spin quantum numbers, since there are both possibilities are present, so we are combining them in the mod of half plus minus half. So when they are added together, we have 1. When they subtract, we have 0. So 1 and 0 will be the total, are the two possible values for the spin quantum number of the helium atom in its first excited state, which is 1s and 2s state. And if you want to calculate the multiplicity, which is given by capital M is equal to S plus 1, you have now two values of S are possible. One value is 1, the other value is 0. You can put these two values over 0 and you can get multiplicity is equal to 3 and 1. So 3 mean triplet states and 1 mean singlet state. And now you can also calculate the value of J using the previous formula, that's the LS coupling formula, which gives you capital J, that is the total quantum number of the atom is equal to mod of L plus minus S. So now you have the value of L, which is 0, but now the S has two values, 1 and 0, which I have written them in the form of a bracket inside the mod. So you can have two values over here, and with these two values adding to 1, you have again the two possible values of J. So total quantum number of the atom has two values, 1 and 0. The term corresponding to the excited states are 2, 3s1 to 1s0. Here this 2 and this 2 is the principal quantum number following this terminology. Here n is the principal quantum number, and you see that this is the excited state we are talking about, where the principal quantum number is 2. So we have written 2 over here, and this is the multiplicity. Multiplicity have two possibilities, 3 and 1. So I have written 3 over here, I have written 1 over here, and this capital S is the term symbol, and this term symbol is the value corresponding to the capital L value, which is 0. So this capital L value is 0, and corresponding to capital L is equal to 0. The term symbol that corresponds to capital L is equal to 0 is capital S. So I have written capital S over here and capital S over here. And here the subscript of this one is 1 and 0, which is the total angular moment, which is the total quantum number of the atom. So these are the term symbols corresponding to the excited states of the helium, the first excited state of the helium. So this one corresponds, this is the term symbol that corresponds when the two electrons have the parallel spins, and this corresponds to the case when they have anti-parallel spin. These are shown in the energy level diagram. So let me show you in the energy level diagram. For example, this one. So this is for the case of the parallel spins, and this is for the case when they have the anti-parallel spins. So you see that the energy diagrams is what I have shown over here, to 1s and to 3s. So these two levels, these are the two levels which correspond to the excitation levels of the first helium neon of the helium atom. And these are the two levels. Neon atom has a total of 10 electrons. Now you see that I have spoken about the ground state of the helium atom and also to the first excited state of the helium atom. And I have found these two are the levels which correspond to the excited states of the helium, first excited state of the helium atom. Now I am going to talk about the neon atom. Neon atom has a total of 10 electrons with the electronic configuration 1s2, 2s2, 2p6. The excited states correspond when one of the p electrons from the 2p6 moves to either s states, and the possible s states are 3s, 4s, 5s, and so on, or to the higher p states, that is the 3p, 4p, and so on. So you see that here the principal quantum number in the ground state for the p orbital is 2p6. So from the 2p6 to you can move either to the s states, which are 3s, 4s, and 5s states, or you can move to the higher p states with the principal quantum numbers 3p, 4p, and so on. So these are the possibilities. In Pastion, so let me show you these levels also so that you can have an idea. So you see that this is the ground state of the neon 1s2, 2s2, 2p6, and these are the possible, this is the first excited states, which is the 3s states, and the other states are also exist. For example, corresponding to this is the 3s state. The next s state is the 4s state, which is over here, and the next to the 4s state is the 5s state. And the p states have been separated. I have written them on the right hand side so that they can be separated from the s states. This is the 3p state and this is the 4p state. So you can see their energies also. That is the 3s is lower in energy than the 4s, and the 4s is lower in energy than the 5s, and you can see that the 4p level is lower in energy than the 5s, and this 3p is lower in energy than the 4s, but 3p is higher in energy than the 3s. And you see that each S level has been shown to split into 4 states, four substates. So here 3S, 4 substates, 4S, 4 substates, 5S, 4 substates, and each P has split into 10 states. You can see these are the 10 substates corresponding to 3P and 4P. In the Pascal or Raka notation, each of the S states is split into 4 sublevels, whereas each of the P state is split into 10 sublevels. The splitting of the neon levels is also shown along with the helium levels. So you can see that I have shown them side by side. These are the helium terms corresponding to the first excited state of the helium, and these are the excited states in the neon. And you can see that I have shown them. That is, for example, the 4s states of the neon is very close, is nearly resonant with the 3s state of the helium, and similarly the 5s state of the neon is very close to the 1s state of the neon of the helium. The other states have also been shown. So we have shown the excited states of the helium and neon side by side. So you can see that which of the neon levels are resonant with the excited states of the helium. S to S transition is forbidden by electronic dipole and spin and thus 3s2, 3s1 and 2s10 are the metastable levels. Due to electron collision, 4s and 5s levels of the neon are directly excited. So let me talk about this one. S to S transition is forbidden by the electronic dipole and spin. So you see that when you have excited the helium through collisional excitation to the 3s level and to the 1s level, then from 1s level to the 3s level, the decay by optical means or by itself is not possible. And also the decay from these excited states to the ground state of the helium atom, for example, this one is not possible because this is forbidden. That's why this is optically forbidden. That's why we call these two levels of the helium atom, that's the 1s2, 1s and the 2, 3s levels. These are the metastable levels of the helium atom. That is, they have much longer lifetime. But you see that their energies are resonant with the 5s and 4s levels of the neon atom. So when the neon atom collides with the helium atom, the transfer of energy occurs from the helium atom to the neon atoms to the corresponding resonant levels. So let me read again. S to S transition is forbidden by electronic dipole and spin, and thus the 2, 3s1 and 2, 1s0 are the metastable levels. Due to electron collision, 4s and 5s levels of the neon can be directly excited. So the neon atoms can be directly excited when there is a collision between the neon atom and the helium atom, because their energies are very much resonant with each other and are very close to each other. So the transfer of energy can easily occur during the collisional process. The excited levels of the helium, which is 2, 3s1 and 2s and 2, 1s0, are nearly resonant with the 4s and the 5s levels of the neon. Thus, during a collision, energy is transferred from the helium to neon atoms, which increases the population inversion significantly in the neon atoms. So you see that these are the upper laser levels of the helium neon laser system in the neon atom, which are the 4s and the 5s levels are the upper state levels in the neon atom for the lasing process. So you can see over here in the diagram, 5s and 4s, these are the upper laser levels. For example, 5s is the upper laser levels for the transitions to the 4p and also to the 3p for the wavelengths 3391 nanometer, 633 nanometer, and 543 nanometer. For these three transitions, the upper level is the 5s level of the neon atom, whereas the for 3391 the lower laser level is the 4p level, and for the other two transitions, that is the 633 nanometer and 543 nanometer, 5s is the upper laser level, whereas the 3p is the lower laser level. And for the 1152 nanometer, 4s will be the upper laser level of the neon atom, and the corresponding lower laser level will be the 3p laser level. So thus during the collision, energy is transferred from the helium to the neon atoms, which increases the population inversion significantly in the neon atoms. That is the population from the helium is transferred, that is the energy from the helium is transferred to the 5s and to the 4s levels of the neon atom. So the population in these two levels of the neon atom will increase. That is the population inversion with respect to their corresponding lower laser level will increase. The 3p and the 4p levels are also directly excited with smaller cross sections compared to the 4s and 5s levels. The lifetime of the S and P levels satisfy the condition for CW operation. Laser transitions occur from the S level, which is the 4s and 5s levels, to the P levels, which are the 3p and the 4p levels. So you see that the excitation from the neon atom, when the electrons collide with the neon atoms, the neon atom can also be excited to this 3s level, to the 4s level, to the 5s level, or correspondingly to the other p levels, for example to the 3p levels and to the 4p levels. That is the neon atom, while it have a collision with the electrons, can also get excited directly by taking energy from the kinetic energy of the electron, and can be excited to these possible states, that is to the 3s state, 4s state, 5s state, and also to the p states, which are the 3p and 4p states. And you know that for this one, the excitation will occur, but the cross section of these excitations is not very high. So in order to make the population inversion to be increased dramatically, which is the requirement for a CW laser operation, what we need to do is that we need to increase the population inversion of the 5s and the 4s level with corresponding to their lower laser levels. For that one, we need a helium atom to be excited in these two levels, because the energies of the helium will match with that of these corresponding levels. That is these two levels of the helium in their first excited level are in resonant with the energies of the 5s and 4s levels of the neon atoms. So the energy will transfer from to these neon atoms. So the other possibility that I have discussed, that the excitation from the neon ground state to these states is also possible, but with comparatively much lower cross section. To select a particular wavelength to laser dominantly, wavelength must match with the peak reflectivity of the multi-layer dielectric mirror. So you see that this is very important. You are using a multi-layer dielectric mirror which will help you to select the required wavelengths. And you see that in this operation we are talking about the 4 wavelengths from the helium neon laser in the continuous wave operation. So these 4 wavelengths are shown. And one of these 4 wavelengths can be selected using multi-layer dielectric mirrors. To select a particular wavelength to laser dominantly, the wavelength must match with the peak reflectivity of the multi-layer dielectric mirror. The natural broadening is found to be delta nu natural is equal to 1 over 2 pi tau, which is equal to approximately equal to 19 megahertz. So this is 19 megahertz is actually the natural broadening of these wavelengths which are emitted. And this tau is given by 1 over tau is equal to 1 over tau s plus 1 over tau p, where the magnitude of tau s is of the order of 100 nanosecond and the magnitude of tau p is of the order of 10 nanoseconds. Actually, these are actually the lifetimes of the S level, S state, and the lifetime of the P states have been written. You know that the lifetime of the S states is approximately 10 times longer than the lifetime of the corresponding P states. So the lifetime of these S states of the upper laser level corresponding to their lower laser levels is 10 times higher. So that's why the population inversion is achieved for a continuous operation which is required from the helium neon laser. and this matches the requirement for the continuous wave operation for the helium neon laser. That's why the S states, which are the upper laser states for the helium neon laser system, has much longer lifetime in comparison with the lower states of the laser levels, which is of the order of which is just 10 nanosecond. So these tau S and tau P are respectively the lifetimes of the S and P states. Some important transitions are now shown. For example, 5S to 4P. This occurs at 3391 nanometer, and this is in the infrared. From 5S to 3P at 632.8 nanometer is the red wavelength, is in red. And from 5S to 3P at 543 nanometer is in green. And from 4S to 3P at 1152 nanometer is in IR, infrared. So from the helium neon laser, we have two wavelengths. One is in red, the other is in green. These are the much popular wavelengths from the helium neon laser, and the most popular one is the red one. And these two are in the visible, and whereas the other two are in the infrared. For example, 3391 nanometer is in the far infrared, and this is 1152 nanometer is in the near infrared. So these two are in the infrared, and the other two are in the visible. And the red and green are the most popular, and out of these one, the red one is the most popular one. Line width due to Doppler broadening is approximately 1.5 gigahertz. The magnitude of collision broadening is quite small. That is, delta nu c is of the order of 0.6 megahertz at a gas pressure of half torr. Typical value of partial pressures of helium neon gas mixture is 4 torr of helium and 1 torr of neon. Schematic diagram of helium neon laser cavity is shown in figure number 2. The cathode, let me show you the figure first. Schematic diagram of a helium neon laser cavity indicating its main components. You can see the main components which have been marked: anode connection, spacer, gas reservoir, aluminium housing, gas tube, cathode connection, output beam, output mirror, cylindrical cathode in the form of cylinder, bore support spider. These are the spiders which support this bore. Borosilicate bore. This is the borosilicate bore. Anode. These are the anodes. Brewster window. This is the Brewster window. And the plane mirror. So this is the plane mirror. These are the essential components of a laser cavity, of a helium neon laser tube. The cathode is a large sized hollow cylinder to sustain the impact of ions produced during the discharge. The discharge occurs between the hollow cathode and the ring shaped anode. The main tube is sealed from both ends and acts as a reservoir for the gas mixture. Discharge is mainly confined within the capillary, where the population inversion is mainly achieved. So let me show you. This is the capillary tube, in the center. This is the capillary tube from which at which the lasing action takes place, and the main population inversion occurs in this region. If a linearly polarized beam is required as an output beam, that is, we want to obtain a linearly polarized light from the laser, from the helium neon laser, a glass plate at Brewster angle known as Brewster's window is placed inside the cavity. Let me show you that one. So this is the Brewster window, just in front of the plane mirror. It is shown over here. The two end mirrors are sealed as part of the main glass tube. Hemispherical resonator is a preferred choice because of its stability, easy alignment, and TEM00 mode operation. There is one disadvantage associated with the hemispherical resonator, and that is the volume of the plasma discharge is not fully utilized because the beam spot at the plane mirror is a small fraction of the beam spot at the output concave mirror. An optimized value of current and hence current density is used to obtain fixed and stable output beam. A high value of current density will lead to de-excitation of the excited helium levels through super elastic collision processes. So you see that this is very important. A high value of current density will lead to de-excitation of the excited helium levels through super-elastic collision processes. If K2 represents the de-excitation due to collision with walls and K3 times J represents the de-excitation due to super-elastic collision, then under steady state operation we can write that Nt times K1 times J is equal to K2 plus K3J times N star, where K1J is the excitation rate, K1J is the excitation rate, Nt is the ground state population of the helium atom, and N star is the population of the two 1s0 in the excited state. So this is the population, N star is the population of the excited state of this level, particularly for example to 1s0, and the rest of these terms have been defined where J is the current density. Don't confuse it with the total angular momentum of the atom. Here J stands for the current density. Nt is the total population in the ground state, and N star is the population in the of the excited level to 1s0. And solving this equation for N star, you can see that N star is given by Nt times within the parentheses we have K1J divided by K2 plus K3 times J. As J increases, N star increases, because the value of K3 is not significant in comparison with K1. So K1 is a dominant factor, and when you increase the value of J, that in the numerator becomes dominant with its corresponding counterpart in the denominator, which is K3J. So we can say that as J increases, N star increases and eventually becomes saturated. That is, 1s is saturated, and thus the near resonant levels of the neon, which is 5s of neon, is also saturated. Under no lasing, the lower laser levels, that is the 4p level and the 3p levels, get directly populated from the ground state, and the population linearly increases with J. This is summarized in the figure number 3, which I am going to show you. So under no lasing action, the lower laser levels, which is the 4p level and the 3p level, get directly populated from the ground state, and the population linearly increases with current density. So the current density can also excite these 3p level and the 4p levels of the helium atom. For example, this 3p level and 4p level can also be directly excited if the current density is not optimized. And this is what we are going to show you in the diagram, the impact of current density. Population variation in the upper and lower laser levels as a function of current density. So you see that the current density is plotted on the horizontal axis, where the population is plotted along the vertical axis. So for the upper laser level, you can see that the population will increase with the current density, but not linearly, but quadratically, and is going like that. So this is the population of the upper laser level, which increases with J. And the population of the lower laser level increases linearly with J. So you see that as J increases, the difference between the population level decreases between the upper laser level and the lower laser level. And you see that this is the point which I have marked as J optimum. That is the optimum value of the current density is the value at which the population difference is maximum between the upper laser level and the lower laser level. So this is what we have to choose J opt. Choosing higher value of J can excite the lower atoms, and then of course the population difference will decrease, which we should avoid. Helium neon power supply designs Helium neon power supply designs use optimum current values and thus optimum current density marked as J opt, as shown in figure number 3. PD, pressure times diameter of the capillary tube. PD is equal to, it should vary in the range from 3.6 to 4, and pressure is measured in torr, whereas the diameter D is measured in millimeter, where P is the total pressure and the capital D is the capillary diameter, is an experimentally optimized relationship. So this relationship, that is PD is equal to 3.6 to 4, that is PD should vary in this range. This is an optimized, experimentally optimized parameter. So pH, that is the pressure of the helium, and the ratio of the pressure of the helium to the pressure of neon is of the order of 5 when we want that the lasing should occur at the wavelength of 632.8 nanometer, and the ratio of helium pressure to the neon pressure is of the order of 9 when you want that lambda of equal to 1152 nanometer should laze in the cavity. So these have been determined experimentally, and these are the experimentally optimized results. The constant value of PD, and hence the diameter, which is nearly of the order of 2 millimeter, arise due to optimization of electron temperature in the gas mixture during laser operation. Population of the laser levels is due to electron collision. Population of the laser levels is due to electron collisions, which increases with P or with 1 over D. Thus, for optimum value of a population or the laser gain, the product PD must be constant. So this product PD should be constant, and I have explained that why it should be constant, because population of the laser levels due to electron collision will increase with P or will increase inversely with D. Thus, optimum value of the population or the laser gain medium, the product PD must be constant. As D is decreased below the optimum value, diffraction losses increase, because if you decrease the diameter of the laser tube, the diffraction will increase. Diffraction losses increase largely, and the net gain of the laser goes down its optimum value, because due to diffraction the light will deviate from the rectilinear path which supports the propagation of the laser beam inside the capillary tube. Thus, for optimum net gain, optimum value of capital D is mandatory to obtain a frequency stabilized operation. from a helium neon laser at lambda is equal to 632.8 nanometer, its cavity length is restricted to a maximum value of 20 centimeter, and a single mode of laser operation is achieved. That is the single mode longitudinal operation. This is the single longitudinal mode operation is achieved. To make this mode to coincide with the peak of the gain line, the cavity is tuned. So you see that if your mode is not lying in the center of the gain bandwidth, you can tune the laser cavity. To make this mode to coincide with the peak of the gain line, the cavity is tuned using piezoelectric precision mirror translator. This single longitudinal mode laser can be frequency stabilized to a high degree with a ratio. You can notice that delta nu, the ratio of delta nu to nu is of the order of 10 to the power minus 12, using a frequency reference either from a high Venus Fabry-Paro interferometer or from an absorption line of the iodine line, that is I2 line. Helium neon is a low efficiency device due to low quantum efficiency. An energy of the order of 20 electron volt is required to populate the upper laser level, whereas the laser photons have an energy of the order of 2 electron volt or less than that. So you can see the magnitude of energy required is 10 times larger than the magnitude of photon energy which is obtained. Helium neon is also a low power device with a typical power ranging from 1 to 20 milliwatt with cavity length in the range of 10 to 50 centimeter. The operation at green wavelength is even less powered. The operation of the helium neon laser at 1152 nanometer made it the first gas laser and the first continuous laser operation as well. Helium neon at red wavelength is very popular in academic use due to its safety, low power, and high beam quality. Single mode helium neon has been greatly used in precision displacement measurement as well as in holography. The green helium neon laser is more popular in alignment purposes due to its high visibility. So next we are going to discuss the copper vapor laser. Copper vapor laser. Copper atom has 29 electrons with electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 and 4s1. There is one s electron, that is this one, 4s1 electron. There is one s electron in the outermost shell with quantum number n is equal to 4. You see that here n is equal to 4. Capital L is equal to 0. This is for s electron. For s electron, we have capital L is equal to 0. And capital S, that is the spin, is equal to half, which gives the total angular momentum capital J is equal to mod of L plus minus S is equal to 0 plus minus half is equal to half. And the multiplicity capital M is equal to 2s plus 1. This capital S is actually this value of S from here. That is the total spin quantum number. So putting that value over here, you have multiplicity capital M is equal to 2. That is doublet. The term symbol corresponding to L is equal to 0 is capital S. Since we have L is equal to 0 over here, the term symbol is capital S. Don't confuse this term symbol capital S with the total angular momentum quantum number capital S. This is the total spin quantum number, and this is the term symbol. Term symbol corresponds to the value of the orbital quantum number. Thus, the ground state is represented by the term. So the ground state of the copper atom is represented by 2s half. 2 is multiplicity, S is the term symbol corresponding to capital L is equal to 0, and this half is actually total value of J, total quantum number of the atom in the ground state. The excited state corresponds to the case when 4s electron moves and occupy the 4p orbitals. So you see that the next orbital corresponding to 4s is the 4p orbital. So if you move this 4s electron to the 4p orbital, this could be the one possible excited state. The set of quantum numbers is then n is equal to 4, capital L will be equal to 1, that is the, because we are now have moved the electron to the 4s, so the 4p state. So we have only one electron, so we have capital L is equal to 1. S, again the spin quantum number is a half, which gives the total angular momentum quantum number of the atom to be equal to capital J. Capital J is equal to mod of capital L plus minus capital S, and then we have 1 plus minus half. The two possibilities are that we have two possible values of capital J, that is 3 by 2 and 1 by 2, which corresponds to multiplicity. With the corresponding multiplicity, capital M is equal to 2s plus 1, and here S is the spin quantum number, which is half. Substituting that value over here, we have capital M is equal to 2. So double it. So this is the doublet case. It means that we have two values of quantum numbers capital J. The term symbol corresponding to capital L, 1, capital L is equal to 1 is P. So when we have capital L is equal to 0, the term symbol is S. When we have capital L is equal to 1, the term symbol is P. When we have capital L is equal to 2, the term symbol is D. But here in this case we have capital L is equal to 1, so the term symbol is P. Thus the energy terms corresponding to the excited states are 2p3 half and 2p1 half. 2 in with each one is the multiplicity, p is the term symbol corresponding to capital L is equal to 1, and 3 half and 1 half are the values of the total angular momentum quantum number J of the atom. There is another excited state. So this is what we have discussed, one excited state. So when the 4s electron, that is when the 4s electron from here, this 4s electron has moved to the 4p electron, then the two states will arise, and we have written them as 2p3 half and 2p1 half. There is another excited state with slightly lower energy in which one electron from the 3d moves to occupies the 4s orbital. The electronic configuration will then be 3d9 and 4s2. So you see that from this electronic configuration, we can move one of the electrons from the 3d10 to the 4s, so it becomes a 4s2, that is the s orbital. 4s orbital is completely occupied, and then you see that we have 3d9 over here, that is there is one vacancy left over here. So in that case we shall have the electronic configurations 3d9 and 4s2. This is the second excited possibility of the second excited states that we are going to discuss for the copper atom. A missing electron in the 3d orbital will behave as a single hole and is subject to LS coupling to 3d1. So the coupling to a missing hole, to a missing electron, which is regarded as a single hole, can also be treated as if a single electron is present in the 3d orbital. So we can apply the LS coupling to the 3d1, which has a quantum number capital L is equal to 2, because this capital L2 belongs to d orbital, and S is equal to half since we have only single electron. So for the single electron, the total spin quantum number is half, which gives the total angular momentum quantum number J of the atom is capital J is equal to mod of L plus minus half, and we have two value of L and plus minus half value of the spin quantum number. So we have two possibilities, 5 by 2 and 3 by 2, and the multiplicity is M is equal to 2s plus 1. So the multiplicity is 2, that is the doublet, which means that we shall have two values of capital J. And you see that due to the doublet we have two values of capital J, that is 5 half and 3 half. So you see that now corresponding to two possible excited states of the copper atom we have discussed. So this is one excited state when one of the 4s electron was moved to the 4p electron, and this is the second excited state when one of the 3d electron was moved to the 4s. So that becomes a 4s2, and only one vacancy is left in the 3d, which we treated as the presence of single electron there. So these are the two states that we are two excited states. And the transitions between these two excited states will occur to produce two wavelengths. One is from 2p half to 2d3 half. So that will be 578 nanometer. The other one from 2p3 half to 2d5 half, that will be 510 nanometer green. Now you see that we have not just let's talk about these d states. The energy term corresponding to this state is 2d5 half and 2d3 half. Corresponding to what? Corresponding to 3d1. 3d1, because 3d1 is equivalent to the 3d9. 3d9 is equivalent to the presence of one hole, and one hole can be treated as the 3d1, that is the presence of one electron in the 3d orbital. So using this one, we have applied the LS coupling. We have obtained the value of total angular momentum, capital J, to be equal to 5 half and 3 half, and multiplicity is 2. So, and the term symbol corresponding to L is equal to 2. The term symbol corresponding to L is equal to 2 is capital D. So we have capital D over here. So the energy terms corresponding to the states are 2d5 half, 2 with each of capital D is the multiplicity. D is actually the term symbol corresponding to capital L is equal to 2, and capital J is 5 half and 3 half. So we have two term symbols. The ground and the two excited states of the copper atom have been shown in figure number 4. So you can see over here, figure number 4. The caption of the figure is indication of laser transition in a copper vapor laser. So the ground state of the copper is 2s half, which we have discussed. And the two excited states, which I have also discussed them. This is the first excited state with energy terms 2p3 half and 2p1 half. And another excited state has energy terms 2d3 half and 2d5 half. And the two transitions have been shown. One is in green with the wavelength 510 nanometer. The other one is in yellow with a wavelength 578 nanometer. So these are only the possible transitions, because we shall going to discuss why these two only. The electron impact cross section to p states is much higher than to the d states. So see, when the copper atoms interact with the excited electrons, there is a high probability, and the cross section is very higher. That is, the impact cross section is very high for these p states, whereas it is relatively lower for the d states. So it is less. So there are less chances that these states will be occupied through the electron impact cross section. However, there are very high possibility that these two p states are occupied due to high value of impact cross section for the p states. So the electron impact cross section to the p states is much higher than the d states. P states are thus easily populated. So the population inversion is achieved between these two p states in relevance with the d states, which are the lower laser levels, and these two are the upper laser levels. From 2p 3 half, 1 half to 2s 1 half, that is to the ground state, are allowed under optical transitions. That is, from these 2p states to this ground state, the optical transition is allowed under the condition that delta J, that should be equal to 0 plus minus 1. That is, the total quantum number of the atom should change either to 0 value, or to the value of a plus 1, or to the value of a minus 1. If this happens when the transitions from 2p3 half and 2p1 half to the ground level of the copper atom, which is 2s half, is considered under the allowed selection rule. Delta J is equal to 0 plus minus half. But why we have not shown the transitions from this one? At a vapor pressure of 0.1 torr, the photon emitted under the transitions from 2p to 2s, that is from the excited states to the ground state of the copper, are reabsorbed. That is, when the transition from P to S occurs, the transition from S to P also occurs. That is, the reabsorption of the photon takes place. That is 2s to 2p and 2p to 2s backward. So this is a two directional transition are completely trapped, and the photons is completely trapped between these two transitions. Thus we need to consider from 2p to 2d transitions as the decay mechanism of the p states. So we would prefer that the transition from 2p to 2d state should occur. This is an optically allowed transition, but with weak cross section and with much longer decay time, which is of the order of 0.5 microsecond. The two p states can gain significant population during the pumping process, and thus stands at the upper laser level with 2D as the lower laser level. The allowed transitions with green from 2p3 half to 2pd 5 half and yellow from 2p1 half to 2d3 half wavelengths are shown in the figure, which are over here. So we have shown the green transition and we have also shown the yellow transition. So we don't, this is the preferred transitions because the two p states will occur as the upper laser level, and these two are the lower laser levels, and the population inversion is achieved between these two levels, where the population inversion between these two p levels to the ground states is not achievable. The optical transition from 2D to 2S are forbidden. So optically, this is forbidden from 2D to 2S. And moreover, the lifetime of 2D states is much longer, a few tens of microsecond. The lasing action is self-terminating. Due to longer lifetime of the D states, the continuous operation is not possible. And only pulsed copper vapor laser is possible under pulsed pumping. So we cannot obtain a continuous laser operation with a copper atoms. So copper vapor laser can only work in the pulsed mode because the lifetime of these states is very high. So the self-termination of the lasing action will take place. So only the population in these upper states can be achieved, can be once achieved through the pulsed pumping technique, and then of course the decay to these states will occur, and continuous lasing action is not possible. Only the pulsed laser copper vapor laser is possible. So let me read again. The optical transition from 2D to 2S are forbidden, and moreover, the lifetime of the 2D states is much longer, a few tens of a microsecond. The lasing action is self-terminating, that is the CW operation is not possible, and only the pulsed copper vapor laser is possible under the pulsed pumping, that is the decay of 2D to 2S is through electron impact, that is the super-elastic collision. That is the transition, that is the decay from these states to the ground state, that is from these two D levels to this ground state is only possible through electron impact, which is regarded as the super elastic collision. The decay rate from 2D to 2S sets an upper limit to the repetition rate of the laser pulses, because unless this D level becomes empty, the next pulse from the copper vapor laser cannot be achieved. So the achievement is only possible when D level is empty. In comparison, that is the level, that is the population in these D levels is relatively lower in comparison with the upper laser level, which is the P states level. So the decay rate from 2D to 2S sets an upper limit because we want this level to be empty, relatively empty in comparison in the upper P states, so that the next laser pulse can be obtained. So this will set the upper laser limit. This transition, that is from 2D to 2S, will set up the upper limit to the repetition rate of the laser pulses. The schematic diagram of the copper vapor laser is shown in figure number 5. That is this figure. So this is the schematic diagram of the copper vapor laser, and its main components are shown. So this is the output beam coming out from the cavity, And this is one of the mirrors from the front mirror. This is the vacuum chamber, ceramic tube. This one is the ceramic tube, copper charge shown over here, insulation, mirror, another mirror. And you see that mirror, window, and electrode, they will also be repeated on the other side. Mirror, window, electrode. Similarly, mirror, window, electrode on the front side. And you see that the buffer gas flows over here inside this tube. This is the thyratron. This is the triggering system. So for the pulse pumping, this mechanism is used. Triggering and the thyratron are used for the pulsed pumping system. The copper vapors are contained in the alumina tube. Vacuum envelope thermally isolates the main chamber. Vapors are excited by passing pulsed currents between the electrodes respectively. Power dissipated by the flowing current sets up a value of temperature in the chamber. Anode and cathode are in the form of rings. They are placed at the ends of the ceramic tube. Typical values of neon buffer gas are in the range from 20 to 50 torr. That is, neon as a buffer gas is used and are used to maintain appropriate electron density. The collision of copper vapors in the 2D state with the electrons helps in the de-excitation of 2D states through superelastic collisions. Let me read again. The collision of the copper vapors in the 2D state with the electrons helps in the de-excitation of 2D states through superelastic collision. To minimize the deposition of copper vapors on the glass windows, the flow of neon gas is very important as it shortens the diffusion length of the copper vapors, minimizing the vapors approach to the windows. Copper vapor laser with optical power more than 100 watt have been produced with pulse duration in the range from 30 to 50 nanosecond and a pulse repetition rate up to 10 kilohertz. The efficiency of these systems is less than 4%. This high value is due to high quantum efficiency and high electron impact cross section of the 2s to 2p transition, that is from the ground to the p state transitions. Copper vapor lasers have been used in high speed flash photography of fast moving objects such as bullets. In uranium-235 isotope separation project, many copper vapor lasers have been combined and used successfully. Some important transitions are given from 2p3 half to 2d5 half. 510 nanometer is emitted in the green wavelength, and from 2p 1 half to 2d 3 half, 570 nanometer wavelength corresponding to yellow color is emitted. So you see that I have explained helium neon laser and copper vapor laser. Copper vapor laser is a pulsed laser, whereas a helium neon laser is a continuous wave laser. Both are the gas lasers, and I have discussed the detail of these two laser systems. So this is the end of slide number 136.